Okay, I think it's time to get started. Welcome back, everybody. So, as promised, today I want to talk about the final exam and just do some review stuff. So, I have prepared a review sheet, and you can see it from our class website. I will put a link in the chat, though, so you don't have to find it yourself. But you can go find it, later on. It'll still be there. So I just put a link in the chat to a PDF of the review sheet. What can I say about the final? It's going to be Tuesday, December 15th. That's a week from yesterday. Is that right? Is December 15th a Tuesday? Yeah. Yes, that's right. It's going to, so every final exam is scheduled for 3 hours. That means in theory I could make the test like 3 times longer than our in-class exams, but it will not be that long. You should expect maybe 1.5 times the length of our ordinary in-class tests, just because I don't think there's any point in making you take a super long test. The new material will be the focus of at least 1/3 of this exam. So the new material, that is just the stuff we've done in the past 2 weeks. You should expect that that will make up 1/3 of the test, and then the other 2/3 of the test will be kind of anything goes from the whole semester. So what I want to do today is just go over examples of whatever you guys want to talk about. Probably the old stuff, you will want to refresh your memory, and we can do examples from the old sections. If we are still going to have a quiz and a homework due on Friday, and class time on Friday, I'm gonna spend, we will be working on this week's material. So we could do stuff today from this week, but I kind of intended for this time to be older stuff. Anyway, what do you want to talk about? Anybody have any like logistical questions first of all, or questions about the test as a whole?
I have a question.
Yeah.
So when you say new stuff, what is that, just this week and last week, or?
Yeah, that's right. And if you look at the review sheet, you will see a clear demarcation of the old stuff and the new stuff. So like the last page on the review sheet is the new stuff. Any other simple questions? You will also see on the last page of the review sheet there's a list of formulas that I'm going to give you on the test. I'm going to just write those on the test exactly like they are. So I'm not necessarily going to tell you what they mean or what they're used for. The first one that you can see there is the definition of the derivative. And then you have a bunch of formulas for exponential functions, derivatives and antiderivatives. And then you got, at the bottom there are the trapezoid rule and the Simpson's rule. There are a few things that you need to, I suppose, memorize in terms of formulas, although I guess you need to know the product rule, the quotient rule, the chain rule. I hope you still know those. Probably those are the only other sort of formula-like things that I will expect you to have memorized. Any other simple, basic questions?
Is there going to be an answer key to the review sheet?
No, I haven't written up answers to these. So actually, the review sheet, I don't know if you noticed, the old material of the review sheet I just copied from our previous review sheets for the other exams. So those are the same questions. Yeah, I haven't written out answers to them. What I've done, in the past, people always, earlier in the semester, asked me about the answers. If you work them out, I would be happy to take a look at what you got. Just send me a picture of your paper, and I'll let you know how you're doing.
Okay, thank you.
Any other questions? All right, maybe we can go over some of this stuff. Is anybody, take a moment to look at the sheet there, but anybody want to shout out something that that you would like to go over? I didn't prepare any particular examples, but if you see something on the sheet that doesn't look familiar to you, maybe something you've forgotten how to do, I'd be happy to do one.
Can you do a couple of the exponentials and logs, the derivative of exponentials and logs?
Sure, yeah. Derivatives of exponentials and logs. So, oh yeah, actually this reminds me, there were other formulas that I didn't put in that list there that I really should have. At the end there, you don't see formulas for the derivatives of logs. So let me just, I'm going to tell you those on the paper also. So I'll add these to the paper. Derivative of natural log x. This is 1 over x. I hope you remember that, but this one maybe you don't remember. Derivative of log with some other base of x is 1 over x, natural log of a. So these two formulas will also be given to you on the test. Sorry, I neglected to put them in the on the review sheet. I'll add them in after class, and if you reload that page, you'll see those in there. Okay, yeah, so you'll be given those formulas. So when it comes to, on the test, doing derivatives of exponentials and logs, it will mostly be a matter of identifying the correct formulas to plug into and then making sure you do the chain rule appropriately. So I'm just going to make up a few. How about, let's do derivative of, how about e to the 3x squared? I'm just going to write a bunch of them down here. 3 to the 4x, derivative of log base 5 of x squared plus x. Let's just do these, and then yeah, I'll make one more. X squared. How about x squared ln of 3x? Okay, let's just go down the list here. So the first one, e to the 3x squared. So the appropriate rule that you want to use for that one is just about the derivative of e to the x is e to the x. So that means when you take the derivative of e to something, what you get is just the same thing again. So I get the same thing again. But then, when you're using these formulas, you always have to remember to do the chain rule. So this formula that I wrote over here, this is correct as written. And when you're using this formula, you would just do exactly this if it was just x inside the exponent. But whenever you have anything more complicated inside the exponent, you additionally need to do the chain rule, which says multiply times the derivative of the inside. So now I go times the derivative of the inside of the exponent. Somebody want to shout it out? What's that going to be?
(6x).
6x. Yeah, thank you. All right, so that's the answer for the first one there. That's not so difficult, right? The second one is similarly easy, although you got to make sure you use the correct formula. So for the second one, the correct formula is derivative of a to the x is a to the x ln a. So when I do this derivative, I'm using that formula that I just wrote on the right side there, where instead of a, playing the role of a is the number 3, and instead of x, it's 4x. So what I get is 3 to the 4x again, times ln of 3. I just did this over here. Derivative of some number to something is that same thing again, and then times ln of whatever the number is. And then, as before, I got to do the chain rule times the derivative of the inside of the exponent. Derivative of 4x is 4. Hope you remember how to do the derivative. It's like the antiderivative. Okay, so this is the derivative of 3 to the power 4x. Any thoughts about that one? I hope it's coming back to you. I know we haven't done these in a while. All right, the next one, log base 5 of x squared plus x. So for this one, the appropriate formula would be derivative of log base a of x, which is 1 over x ln a. That's something I just wrote. Okay, let's do it. So what this says is when you have log with some other base, which is 5 in this case, I'm using 5 for a over here. I get 1 over whatever this stuff was, so it'll be 1 over all of that. X squared plus x times ln of 5. Right. So I'm using that formula over there. A is 5, and instead of x, I have x squared plus x. And now, as always, I got to do the chain rule. I multiply this whole thing, and this is not part of the denominator anymore. It's just multiplied on the side, times the derivative of the inside of the parentheses. Someone tell me what's that going to be?
2x plus 1.
2x plus 1. Great. And you better put the parentheses around that because the multiplication on the outside needs to distribute. All right. That's how we do it for that one. Okay, and the last one, x squared ln of 3x. So as part of this, we're going to use the derivative of ln of x is 1 over x. How do we handle the x squared in the front? Any thoughts about that?
Is it just like... Go ahead.
Go ahead, Jordan.
Does it just stay out front there?
It does not just stay out front there, unfortunately. If it were a number, a coefficient, then it would just stay on the front as a coefficient. But when it's not a number, when it's got an x in it, you got to do something a little fancier. There's a little hint. There's a little dot there, right? They're being multiplied.
Is it chain rule?
The product rule. I heard somebody say the product rule. Yeah, you got multiplication here, and so you must do the product rule. So this one is, I mean, when you write it down, the answer is going to be more complicated than those other ones. I hope you remember the product rule. The first thing, as it is, so the first thing is x squared, right? And the second thing is ln of 3x. We are going to do the first thing like it is, which is x squared, times derivative of the second part. Derivative of ln 3x is, using the formula over there, 1 over 3x, and then I do the chain rule, times 3, right? That's the derivative of ln 3x. Derivative of ln is something, you go 1 over that thing, and then you do the chain rule. You multiply times the derivative of the inside of the parentheses, which in this case was 3. Okay, this was only half of the product rule. Now I go plus the second thing like it is, which is ln 3x, times derivative of the first thing, which is 2x. And this is the derivative of that thing. Right? That's how we do it. Any thoughts about any of those? I hope this is along the lines of what whoever asked me to do these. I hope that's what you wanted to see.
Yeah, thank you.
All right, what else?
Could we do a use substitution problem?
Sure. Yeah, those are tricky, and actually, there are several ones on the homework this week which involve use substitutions. So, you'll want to do the use substitutions. Do you want to do one? Let's do one with the definite integral, just because that is relevant to this week's assignment. How about integral from 4 to 7 of 5x over x squared plus 1, the square root. This will be great. So when you look at this, you should first try to do it without a u substitution, or at least think about, do I really have to do the u substitution? Because on the test, I'm not likely to tell you to do the u substitution. And this, you know, some people realize on the latest exam, on exam 3, there was one which required a u substitution, even though I didn't tell you, and a lot of people didn't realize that they had to do the substitution. But looking at this, you will see that it is too complicated to do with any simpler tricks. You can't just take the integral on the top and also the integral on the bottom. That's not allowed. And you can't. There isn't any other sort of more convenient way to rewrite this, simplify it. You got to do the u substitution. So let's try it out. What do you think? What should I choose for the u?
X squared plus 1.
X squared plus 1. I like that. Remember, your general strategy is to choose the u to be the inside of something. Maybe the inside of parentheses. Maybe the inside of exponent. Inside of a square root sign, which is what we've done in this case. All right. Then you find the du, which is 2x dx. Du, remember, is always the derivative of u, and you always include dx as part of the du. And then when the du has a constant in front of it, which it often does, it is usually helpful to divide that constant to the other side. 1/2 du equals x dx. All right, I just divided the 2 from the previous equation. Divide the 2 onto the other side. 1/2 du equals x dx. All right, let's try to actually plug this stuff in. Whoa. Something weird is happening. Am I all right? What? Sorry, something funny is happening with my my recording here. I know. All right, I think it's working. Okay, sorry. Let's start doing the substitution. I'm going to plug in, first of all, plug in for the u, just where the u goes. The u is right there, so I'm going to plug in, first of all, 5x over the square root of u dx, right? And now I would like to, of course, our goal is to use only u's in there, no x's. So what I typically do at this step is to try and sort of separate apart the u stuff from the x stuff. So I'm going to do integral, in here I'm going to write this, break up the fraction like that. Like so. Right. The point of that is just to separate the u away from the x's just when we write it so that we can tell what we got to do with the x's. Here we have 5x dx. Now the 5 is not really important. Remember, you can always take a constant out of an integral, so we might as well bring the 5 out also. 1 over root u times x dx. And now, what can we do with x dx? This right here is the same as this. It is 1/2 du. See, x dx is 1/2 du. So, I plug it in. I got 5 here, integral. 1 over root u times 1/2 du. And then the last step before I actually do the integral is I'm going to take that 1/2 out of the integral also. Factor the constant out. It will multiply onto the 5, so I get 5 over 2. Integral 1 over square root u du. All right. This is a maybe slightly tricky u substitution. I don't know. We're not done yet. You got to actually do the antiderivative of 1 over square root of u. Anybody have a suggestion about that? Perhaps we could write that in a more convenient way in order to do the antiderivative. One over square root of u.
You would make it u to the 1/2.
Yeah, how about u to the minus 1/2 because it's in a denominator? I mean, you could write 1 over u to the 1/2, but really it's might as well go all the way here. It is u to the negative 1/2 because the 1/2 because it was a square root and the negative because it was in the denominator. All right, and now we can do the antiderivative by increasing the power by 1 and then dividing in front by the new exponent. So what I have is the 5/2 will just stay like it is, and then the new power is going to be -1/2. When I increase by 1, it becomes +1/2, and I divide by that. So it looks like this. Now, ordinarily I would put the plus c, but since this is a definite integral with the little the two little numbers, I'm not going to put the plus c. All right. Okay, we have done the antiderivative. That's why I'm not writing the integral sign anymore. Final step of the u substitution is just to replace the x's in where u is. So this becomes, would you mind if I combine these constants out front? 2 times 1/2 in the denominator will just cancel, right? You'll get a 1 in the denominator. So this ends up just being 5. And then u to the 1/2 looks like x squared plus 1 to the 1/2. All right? So I replace the u by what it is in terms of x. And then I simplified the constant coefficients. All right? And now, finally, I'm going to plug in fundamental theorem of calculus. Since this is a definite integral, I need to plug the 2 values in, the 7 and the 4. So let's do it. First I plug the 7. I get 5 times 7 squared plus 1 to the 1/2 minus, now I plug in the 4. 5 times 4 squared plus 1 to the 1/2. There you go. That's my answer. Not terribly easy, I would say. These ones you definitely need to practice them. Anybody got questions about that one? You'll have a chance to do more like this on your homework this week. All right, what else should we do?
Can we do a total change theorem problem?
Sure. So these were like last week. People, for the most part, by the way, did very well on the quiz last week. The total change, so these are usually going to be word problems. You know, the one on the quiz was about like my bank account goes up and down every day, and I find the total change over a certain amount of time. Let's say my my height is increasing. Let's say I'm a nice growing boy. Over time. Let's say like this is going to be completely fictional. I'm going to just make up an equation here which doesn't actually resemble how my height grows. Let's say 0.05, I'll call this h of t equals 0.05 t squared plus 0.1 t, where t is in years and the height is in feet. I don't know. This is totally made up. Not accurate at all. Oh, but I meant to say h prime. All right. This tells you how my height changes from year to year. All right. So actually, yeah, whatever. This is completely made up formula here. I could ask you something like, find the total change in height from year 1 to 5 as a tiny tot. Sorry, I'm off under the head there. How much did I grow in total from year 1 to 5? And I could say, let's say part A, estimate. I put an extra I in there. Estimate using n equals 4 and the midpoints. And then maybe part B, find the actual value, like not an estimation, but the true answer. All right. Okay, so for part A, estimate using n equals 4 and the midpoints, you would, so let's do part A first. You would draw out the little interval, which goes from 1 to 5. And I said n equals 4, so I should divide this into 4 bits, which nicely divides up into 1, 2, 3, 4, 5. And I said use the midpoints. So those are these numbers here. These guys, right? They are, you know, 1.5, 2.5, etc. So for this one, my estimation would be, and what's the delta x in this case? It would be the width of the little intervals, which is just 1 in this case. If you like, you could do b minus a over n. You get 5 minus 1 over 4, which is 1. All right? So for the midpoints then, which is what I told you to do, you would do, you know, the delta x on the outside, which is just 1 in this case, and then I do f of 1.5, f of 2.5, f of 3.5, f of 4.5, where I suppose I don't really mean f, I mean this function up there, which I called h prime above. And so my final answer for this one would be, can't see it anymore, 0.05 times 1.5 squared plus 0.1 times 1.5. That was f of 1.5. I plugged 1.5 in for t in the original thing there, and then plus, etc. All these, the last one should say 0.05 times 4.5 squared plus 0.1 times 4.5. All right? This is an estimation using the midpoints. All right. Any questions about that? I used the midpoints. Okay, and then, is that a question?
Yeah. If you just gave us an equation, would we have to find the derivative and then do that process?
No. So the point of the total change theorem, it says that the total change is equal to the definite integral of the derivative. So if you're going to use the total change theorem, you should be operating on the derivative. I wouldn't ask you, I mean, if I told you the function itself and asked for the total change of the function, you would just subtract two values of it, the final value minus the initial value. But that would be, I would view that as kind of a trick question, and I wouldn't ask you that, because that would just confuse everybody if I didn't give you derivative. And I don't, I suppose I could do that, but I don't usually like doing that. Okay, that was part A, estimate using the midpoints. Part B, find the actual value of the total change. You know, the total change is the definite integral. So can we, not estimating, but actually find the true value of the definite integral? It would be this, the integral from 1 to 5 of this same function, 0.05 t squared plus 0.1 t dt, right? This would be the answer for part B, where you would actually find the real answer, not estimating. And how would we find the real answer? Well, this is a definite integral. You would use the fundamental theorem of calculus, which is the topic of this week. So I would do the integral here. 0.05 stays like it is. T squared becomes 1/3 t cubed, and then plus 0.1. T becomes 1/2 t squared, and then I plug in 1 and 5. So I go through and plug in the 5 first. 0.05 times 1/3 times just 5. 5 cubed plus 0.1 times 1/2 times 5 squared, and then minus 0.05 times 1/3 times 1 cubed plus 0.1 times 1/2 times 1 squared. That's the true answer. And if you're in the calculator business, you could just to as sort of a sanity check, if you plug these two answers into your calculator, this whole thing and this whole thing, they look totally different, but the two answers should be close together, because the first one here, this part A, is an estimation of this one here. So if you were to plug them into your calculator, you should get not the same answer, but close to the same answer. All right, what else we got? We got about 20 more minutes. I'm good for it.
Can we do some antiderivative problems, just like regular ones?
Sure. So antiderivative, I guess you mean like without the u substitution or something, the simpler ones?
Yeah, that's what I mean.
So let's try, I'm just going to make up a bunch of them here. All right, let's try these three. Maybe I should have. Let's see if I can do this. This is going to be fancy if it works. I didn't want a copy of it. I wanted to just write this down here. All right, just so I can write underneath the problem. How about that first one there? So what you have here is a bunch of things that all look kind of similar, although they, you're going to have to use different approaches to do each of these antiderivatives. So 3x squared, this is the easiest of them all. This is just the ordinary power of x. You leave the coefficient like it is, and then I change x squared into 1/3 x cubed. I increase the power by 1, and I divide by the new exponent in the front. And the old coefficient just remains as a coefficient in the answer. Okay, what about 2 to the power 3x? When you see x inside the exponent, that means you're going to have to use the rules for exponential functions. And like I said, these will be given to you on the test. So the appropriate one to use for that, 2 to the 3x, is integral of a to the kx. Because I have a number down here, this 2 is playing the role of a, and then I also have a coefficient inside the exponent, this 3, which is going to be the k. Anyway, the formula that you will see on the sheet is 1/k ln a to the kx. All right? That's a x there. So what do we get here? 2 to the power 3x, just plugging in appropriately to the formula, shall become 1/k is 3, a is 2. So this is, what? I wrote k. 3 ln 2. And then I get a to the kx again, which is 2 to the 3x. All right. So that was this part, right? And then lastly, 3 times 2 to the x. So for this one, the 3 is just a coefficient. This is actually easier than the previous one. The 3 is just a coefficient, and so the 3 will simply remain as a coefficient in my answer. And then what do you do with 2 to the x? Well, that's just like this, integral of a to the x. And so this, again, you'll be given this formula, 1/ln a to the x. And so this becomes 1/ln 2 to the x. Like that. And of course, you got to put the plus c. So that's what this one does. All right. Any thoughts about that? So this doesn't really require any special tricks. It's just a matter of plugging into the correct formulas, identifying and doing it. Okay, how about this next one? X squared plus 1, the whole thing squared. To be honest, when I look at this one, I am tempted to do the u substitution, just because when you see something with parentheses, with like something on the inside of something else, u substitution should come to your mind as the trick to do. Although in this particular case, the u substitution will not work. It's because there isn't another thing hanging out there to play the role of the du. Anybody have a different idea that we can do with this one? Actually, the u substitution is not required. You can do this with a simpler trick. What do you think? Here's a hint. This, of course, is the same as that, right? Anybody like that?
So it's a product rule?
No, the product rule is something you only do for the derivative. Here I'm doing the antiderivative, in which case we don't have something like the product rule we can use. There's actually something we can do to simplify the inside. I'm gonna just multiply out the inside. Do like the FOIL on the inside. So here, still writing the integral sign because I'm not doing the derivative. I'm not doing the antiderivative yet, but I'm just going to do the FOIL on the inside. You know this thing? Right? Did I do? I drew the same arrow twice. You know what I mean? The FOIL thing, right? There we go. So when we do the first things, I go x squared times x squared is x to the 4. I do the inside, I get x squared. I do the outside, I also get x squared, and then I do the last ones, I get 1, right? This is the FOIL. And now it's just a polynomial there, and now you can do the antiderivative easily. You just go down the list there and do the thing with the exponents each time. 1/5 x to the 5 plus 1/3 x to the 3rd plus another one, 1/3 x to the 3rd, and then plus. What happens to the 1 when I do antiderivative of 1? It is?
One x.
It is, yeah, just x. When you have a constant, it just becomes that same constant times x. And then plus c, of course. All right. So this is an example where you can simplify the inside first, and then the integral becomes easy at the end. All right. Okay, let's do this one here. X, I'm just going to write it again down here. X plus 4x cubed over x squared dx. All right, this one also we will do by simplifying the inside. So there are different ways you can think this through, but I think it's easiest for me to write it like this. We change the division by x squared into multiplication times x to the minus 2. All right, and then we can distribute here. Right? So it's going to be, still writing the integral sign because I didn't do the antiderivative yet. I'm just rearranging, doing some simplifying. X, the first thing, x times x to the minus 2 ends up being x to the minus 1 plus 4x cubed times x to the minus 2 becomes 4x. And now we can do the antiderivatives. What do you get from x to the minus 1? What's the antiderivative x to the minus 1? What do you think? I'll tell you, it's natural log of absolute value x. This is a special antiderivative. Remember the antiderivative of 1 over x, also known as x to the minus 1, is the log of the absolute value of x. All right, and then the 4x becomes 4 times 1/2 x squared plus c. And that's what we get. Hope you remember that ln thing. X to the minus 1, you get the natural log. All right, we got 10 more minutes. I think we got time for at least one more. Unless any follow-ups on that one we just did. No, let's do something else. I thought that somebody was going to ask about the definition of the derivative. This is one from a long time ago. You want to try one of those? Of course you do. Let's try one of those. Let's find f prime of x for, let's do 3x minus x squared. Using the definition of the derivative. If I say that, using the definition of the derivative, this means you need to use that formula with the limit as h goes to 0. Remember that thing? Of course, you know what the answer should be. The answer, this is just to check your answer, f prime of x should be 3 minus 2x, right? Just taking the derivative sort of the easy way, using the power rule, you get 3 minus 2x. So, you know, we'll be able to make sure that we did it right. But your job is to do this using the definition of the derivative. So you have to remember, actually you don't because I'm going to give it to you on the test, but this is the definition of the derivative. F of x plus h minus f of x over h, right? And we are going to, you know, it's a bit of a process. You gotta just keep it straight and try not to mess it up. We should begin by plugging in first for the f. So f of x plus h, and this is the hardest step actually. This is where most people's mistakes will be made right now. F of x plus h, it means you just write this formula again, but you use x plus h instead of x. So it's going to be 3 x plus h minus x plus h squared. All right? I did this formula here, but each time, instead of x, I put x plus h. That's how we do it. And make sure you put the parentheses there. Minus f of x again. All right, 3x minus x squared. Make sure you put those parentheses too, haters. All the parentheses that I wrote there are important, and if you leave any of them out, it means something different. So on this, all divided by h. All right. What should we do next? We should try to expand as much as possible the stuff up top, and eventually a bunch of stuff will cancel. That's our goal. But before the cancellation happens, we need to multiply it out. So let's distribute the 3 there. I got 3x plus 3h. That's easy enough. Minus this x plus h. We need to square that out doing the FOIL. You get x squared plus 2xh plus h squared. All right, I'm a FOIL master, so I just remember that that's what it looks like when you square something. Okay, and then minus at the end, minus 3x plus x squared. I distributed the minus sign because I'm not a hater. Divided by h, of course. All right. I hope you're not being a lim hater either. I wrote the lim every time. That's because I haven't done the limit yet. You don't do the limit until the very end when you plug h equals 0 into this. You can't do it now though because I have h in the denominator. All right. What else can we do? Actually, I can cancel something at this point. 3x and a minus 3x right here. Like that, right? Otherwise, I'm going to have to keep on sort of expanding. Really, the only thing left to do is distribute that minus sign on the parentheses up top. So it becomes 3h minus x squared minus 2xh minus h squared plus x squared on the end. All right? And now we can continue to cancel minus x squared and plus x squared. And I guess that's it. But now that we've canceled that, we can factor the h out of everything on top. So h factors out. What remains is 3 minus 2x minus h, right? The 3 things that remained up top, they all had a h on them, so I can pull the h out to the front. This divided by h. And now these h's can cancel, all right? I hope nobody tried to cancel the h's before. I see a lot of I'm sure they're perfectly nice people, but they do bogus cancels like this. Anybody think of doing that? Can I just cancel the h's there? Those blue ones are bogus. If you want to cancel the denominator, it needs to be something which you can factor out of everything on the top. So don't try to cancel. It's like premature cancellation. Don't do it. Anyway, all that remains then is lim h goes to 0, 3 minus 2x minus h. And now, finally, we can do the limit by plugging in h equals 0. I end up with 3 minus 2x minus 0, which, of course, is 3 minus 2x. And that's what I said the answer was supposed to be, so I know I did it right. All right. This is using the definition of the derivative. This is not super hard, but you have to just be very careful from step to step and make sure you don't mess it up. Fortunately, you'll always know what the answer is supposed to be, so because you can just figure it out using the power rule. So it's just a matter of making sure you really get the right answer. And if you don't get the right answer, you messed it up somehow. Go back and try and figure it out. Any questions about that? You should probably practice those a little bit. All right. Well, we got 2 more minutes on the clock. Anybody have any real quickies? I don't hear any quickies. So I have we can call it a day then. I have my office hours from now until 1, so if anybody does have more questions, hang around and I will be happy to talk more about this or anything else. Once again, I'll say if you are wondering about your grades, if you're thinking about maybe doing the pass-fail thing, let me know. I will tell you what your grades are, even if you're not thinking about the pass-fail thing. All right. Otherwise, I'll see you all on Friday.